The Chemistry of Batteries by John Stewart Leach and Garret.
All batteries are made from electrochemical cells set in series to send electrons out from the negative terminal or anode and back to the positive terminal or cathode. There are two types of batteries, primary and secondary. Primary batteries, such as alkaline or zinc carbon, are the standard one-time use batteries like AAA, AA, or D batteries as shown in the picture below. These reactions cannot be reversed, like the galvanic cell we built. Secondary batteries, such as lithium-ion or lead-acid, are batteries whose reaction within the cell can be easily reversed with voltage. They're commonly known as rechargeable. The first primary battery, an electrochemical cell made from copper and zinc, was invented by Alessandro Volta in 1800. It was capable of producing 1.1 volts per copper and zinc disc pair. The first secondary battery was invented in 1859 by Gaston Plante. It was a rechargeable lead-acid battery. Alkaline batteries. At the anode, there's a reaction between zinc and 2-hydroxide to form zinc oxide, water, and 2 electrons. At the cathode, there's a reaction between 2 manganese dioxide, water, 2 electrons to form manganese oxide and 2-hydroxide. Hydroxide is a spectator ion in these reactions. Carbon is also used in the shells because manganese dioxide is not a good conductor by itself. These are so popular because of the manganese dioxide's purity and activity, producing more than other batteries. It also has a longer shelf life than other primary batteries. The alkaline system is recognized to have several advantages over carbon-zinc type batteries. Not only does it have a longer shelf life, but also has a higher energy density. Zinc-carbon batteries. Unlike the alkaline batteries, at the anode, zinc goes to zinc 2 and 2 electrons. At the cathode, 2 manganese dioxide, 2 electrons, and 2 ammonium chloride goes to manganese oxide and 2 ammonia, water, and 2 chloride. This reaction is not exact, for the mechanism in which the battery operates is quite complex due to the ammonia, but this reaction works. Also commonly known as the Leclanche shells, these are the first wet cells. Unlike the alkaline batteries, there is only one cathode and anode. The zinc being both the anode and the shell, this battery is still used in low-drain electronics. Carbon-zinc batteries provide an economical power source for devices requiring light to moderate drain because of the use of inexpensive materials and their time-proven constructions. Lead-acid batteries. The reaction at the negative plate is lead plus sulfate to make lead sulfate and hydrogen. At the positive plate, lead dioxide and sulfate and 3 hydrogen make lead sulfate and water. These batteries are most effective for current surges and are most commonly seen in motor vehicles. They are another type of secondary battery. The voltage is usually around 2 volts, but overcharging can result in water splitting into gases and ruining the battery. Unlike the other batteries, this battery has plates instead of cathodes and anodes.
Here we have lithium-ion batteries. These are a much more common type of secondary batteries. The Tesla cars made by Elon Musk use lithium-ion batteries as their power source for their engines. In the batteries, you can see in the anode, we have lithium carbide, which can go into carbide, lithium, and an electron. In the cathode, we have cobalt oxide, lithium, and an electron, which can go into lithium cobalt oxide. During discharge, the lithium ions will move from the anode to the cathode, and the reverse is also true. In these batteries, it's easy to see how the electron is transferred in the equilibrium equation I have at the bottom. You can see the electron on both sides, and it just goes back and forth. That's why it can be recharged. It can go in either direction without breaking, like the alkaline batteries would. However, the cell can be overcharged to the point where the atoms get so excited that they take reaction paths that are not the regular ones, and the lithium will go to lithium oxide, which then ruins the battery. So here we have a recording of building the cell. Here you can see we measured the masses of the zinc and copper electrodes, so you could see the change in mass after we left this cell going overnight. They are relatively light, but they work the job. And here we have our copper sulfate, which is in solution of water. The copper sulfate is a solid crystalline which was dissolved into solution. We also have lead nitrate, and although lead nitrate is not necessarily necessary in the reaction because the zinc will plate off of the zinc electrode, I put just a tad bit in anyways just to be sure. Here we have potassium chloride, also a solid in solution of water, to pour on the salt bridge so that it will work. And right now I am just hooking up the electrodes to the voltmeter and putting them in the voltaic cells. For the solution of copper sulfate, we didn't bother trying to make a specific molarity because the cell is so inefficient with the salt bridge being a piece of paper that trying to get concrete calculations from it would be almost impossible. So now I pour the solution of potassium chloride onto our salt bridge. This is a piece of filter paper folded up. So we built this cell because it's quite similar to the cells that you would find in primary batteries. Although in primary batteries, the cells are much more compact and much smaller. For alkaline, they're all stacked on top of each other, whereas for the zinc-carbon battery, it's just one. And here, I finally put the piece of filter paper into solution, and the reaction starts. You can see it because of the presence of voltage. We've got about 0.9596 volts, and that kept going strong all throughout the entire 24 hours we left it running. It settled down at about 0.7, so it was a great success, but we did try some other methods to increase the reaction's efficiency so we could get better results. Here we have a time lapse of the cell going for about 10 minutes. As you can see, the voltage steadily goes down and it seems to settle out at that 0.82 volts. When I came back to look at it later, we weren't able to get a time lapse for a very, very long time, but around this next day, it seemed to settle at about 0.7 and didn't really change from there, and I ended up taking apart the cell at about there. But even after 24 hours, it lasted at a strong 0.7 volts. And the cell was relatively inefficient, but we did try some other variations of the cell to see if we could get some more efficiency. As you can see in this picture, I put two cells in series. This is the exact same layout as the previous cell. There's just two. So now we have two salt bridges, one between the first copper and zinc, and the second copper and zinc. And the electrodes of the middle, zinc and copper, are connected by an alligator clip. And this is just an entire battery. This is how the alkaline batteries are laid out. It's a lot of cells in series, although those are much smaller. And you can see we do get a much higher voltage. It did, in the picture it says negative 1.8, but we did get it to negative 1.9, which is very, very good in terms of efficiency. It's much better than the original version. You can also see where I made one where the beakers were much smaller, so the salt bridge could be submerged in much more solution along with the electrodes, and it was also two in series. And from this, we were able to get pretty close to 2 volts of voltage. So these two variations worked quite well, and that's our experiment we did making our own makeshift battery. So thank you very much for listening to our presentation on the chemistry of batteries. Here are our sources, and we will leave you with some nice outro music.